ish or over 40 tips and tricks. And from that we have compiled a list of top 10, which we'll now go through. I'll invite my colleague Mark, Jehwan, and Ashwani to join me here on the stage. We'll go through these from 10 to 1. So we'll start with Mark, and then Jehwan, Ashwani, and we've saved the best for last, which means I'll finish this off. And then we'll have the QA session. So Mark, please join us and start off.
Okay, good afternoon again. I promise no cartoons this time. We'll start with tip number 10, which is choosing the right loading method. So if we look at the process that we've talked about for FE safe and how it's used in a typical design process, we have three basic inputs. That's the stresses, the materials, and the loading cycle. And we're going to concentrate on the loading cycle for these next few tips. So we have two basic categories of loading. One is time domain and frequency domain. And we've had a few talks on the frequency domain, so we'll just concentrate on the time domain for these tips. There are four basic methods for time domain loading. Three of them are really valid for linear elastic FEA, and in which case FE safe will perform the Neubert plasticity correction for you. And one is valid for either linear elastic or for elastic plastic. And if it's elastic plastic, FE safe knows not to perform the plasticity correction. So these are the four basic methods, and I'm just going to, for simplicity, say these are the ones for elastic. So basically it's superposition of linear results either in the time domain or modal steady state. And in that special case of modal steady state or transient dynamic, FE safe will convert that to the time domain, and at which point it will be equivalent to the superimposed load histories. The single load history is a special case of the superimposed. If you use a single, very simple cycle, you have some options of how you express that load history, either as a time signal, a PSD, or a preprocessed rain flow. So for elastic or elastic plastic, you can use a sequence of FEA solutions. And really, this is the way that if you have gross plasticity in your model, then you want to use this methodology and not have FE safe do a plasticity correction, because the FE safe plasticity correction is for local plasticity and notches, not for gross plasticity. So if you imagine the rocker arm and the engine rotating, say, through two full rotations, and you have a transient solve every 5 degrees for 720 degrees, you can bring that sequence of stresses and strains into FE safe, and FE safe will create a duty cycle at every node for that model. So another thing, tip number 9, is to break your complex duty cycles into multiple blocks. So basically, each block you can consider to be some event in the life of your component or your assembly. And each block could be one of those four methods that I pointed out. And you can mix those methods between blocks, but obviously not within a block. And I want to talk more about the superposition. That's probably one of the most common and powerful methodologies we have for load cycles in FE safe. So if we imagine that we have a suspension component on a car, and we want to look at one of those suspension components or an assembly of them, we can talk about three directions of loads coming from the load: a normal, direction of travel, and a transverse, for instance. So that would be the X, Y, and Z on the left side of those time plots. We can also say that we want to build a duty cycle out of 8 different events. One might be driving down the freeway. One might be driving on a corrugated dirt road. One might be doing a U-turn on a dime, whatever. You can have as many of these events as you want, but for simplicity, we picked 8 of them. We also have to account for the fact that each of those occur at different relative frequencies in a typical duty cycle. So block 2, there might be 100 out of the total life. In block 7, there might be 500 of those events. So the question is, how do we set that up in FE-Safe? And this is just a quick illustration of that. I brought the graph over, or the illustration of the time signals, just to remind you of what we're talking about. So we had 8 events in life, so that means we're going to have 8 blocks in our duty cycle. We had, in this case, 3 directions, or 3 unit load linear static solves, the X, the Y, and the Z. And consequently, we're going to have 8 times 3, or 24 time signals, one for each direction and each block in our duty cycle. And then, of course, we have to remember that we have to account for the relative frequency of these events. So what we're going to do then is we're going to take our X unit load, multiply it from the time signal that we got from either from the field, maybe using true load, or from SimPack, or wherever we got our time signals. We're going to multiply that X unit load times that time signal and bring it into our block. And then we're going to do the same for the Y signal and Y solve, and then for the Z. Now that we brought those 3 in, FE-Safe is going to superimpose those results together for us. We'll have a single transient tensor that we've created from a steady state solve plus our time signals. And then we have now defined our first block. We have to remember that there's a frequency of 100 for this block, so we have to specify that. And did I get that? Yeah, I got that. Okay, so there's the 100. So now we've defined our first block completely. And then we just go through and do that for the other blocks, and we have defined a duty cycle for FE-Safe. And then what we can do when we're done is we can look at the damage that's done in each block, and you can actually create contours for this. I'm just showing graphs. And you can see that for one repeat of each block, that block 1 was, for instance, in this case, the worst. We can also look at the damage over the number of repeats, and we can see that even though block 1 was the worst by itself, due to the number of repeats, block 6 contributed the most damage to the ultimate failure of the component. So you can imagine using something like eyesight that kind of, you could do some stochastic studies and look at envelopes of fatigue life, because from driver to driver, from region to region, or so forth, you're going to get very different relative frequencies for these different blocks in your duty cycle. And then finally, I'll finish up with accounting for residual stress. This is an important feature in FE-Safe. So there's a number of ways to do that. For non-FEA methodologies, you can use material properties. And if you were to go into our database, there's some materials where you'll see that we have different heat treats available, different hardnesses. Some cases we have carburized conditions, and so forth. So that's on the left. On the right, you can actually put in a surface stress. So if you know that you have a shot peen component, you can have a group for that surface that's shot peened, and you can put in a compressive stress to represent that. So that's 2 ways that you can do it very simply. Oops. And then we have the residual data set pair. That's a functionality where you bring in an elastic plastic forming simulation, for instance, and you bring that in specifically as a residual data set, and FE-Safe will then impose the duty cycle on top of that. So that helps you to align your mean stresses, and that duty cycle will be applied around the mean stresses of that residual data set. And then finally, or not finally, there's one more after this. You can use an elastic plastic data set sequence. So if you remember, we said you could have that sequence of solves. Well, you can take into account plasticity directly in your FEA and bring that into FE-Safe and account for your residual stresses. So the final method is a little trick that's kind of interesting. If you have a residual stress and you consider it elastic, what you can do is you can bring it in as one of the superimposed stresses for your duty cycle. And if you notice that the cycles are like 1, 0, 0, 0, 0, 1, 0, 0, those are your cyclic stresses. But the one that we're calling a residual data set, it's 1, 1, 1, 1, so it's not changing, but it is affecting the mean stress. So this is a trick you can use to bring in an elastic result for a residual, and then FESafe will superimpose all that and then do a plasticity correction on the whole thing. So you have to use judgment, which of these you want to use, which one is most effective, which is simplest, and which is most accurate. So you have to weigh all those factors.
All right. So number 7 is the understand how your FEA code extrapolates stresses and strains for the fatigue calculation. Yeah, we got a lot of questions regarding the what kind of location option for the when FESafe reads in the FEA results to be used for the accurate calculation. Then our recommendation is the element nodal, and yeah, we understand that if we use that, then it will increase the ODB size a lot. So we provided the how to reduce the ODB size, just writing the element nodal informations. But for this topic, I will just let you know how the FEA handles those kind of data. So yeah, as you may know, if you do the FEA calculation, all the stresses and strains are calculated on the integration points. That's the only accurate solutions you can get from FEA. And if you put the position equals to nodes parameter when you write an output, then what FEA Abacus does is from the integration point value, we are trying to extrapolate the stress tensor to the element nodal. So for example, the slide on your right-hand side, if you have some node shared by the 4 elements, then when you put position equals to nodes, then that specific node has 4 tensors. And if you specify position as the location of the data set equals to the element nodal in FESafe, then FESafe will read in all those 4 values and do the calculation on those 4 values for that one node. And we do the critical plane search and everything 4 times. And FESafe picks the worst one. But if you have really a big model, then the user's preference was, how about having just the one typical values per node? And you cannot do that in Abacus by using ODB file, but if you use a field file, then you can use that position equals to average at nodes so that the field file contains only one stress tensor per node. And so if you compare with the position equals to nodes and the nodes in the ODB file and position equals to average at nodes in field file, you have for this example on your left, in case of the position equals to nodes, you have 4 tensors for that specific node, as I said before. And if you use position equals to average at nodes, then you have only 1 tensor. But that tensor is averaged by the tensorial averaging. So that stress tensor can be like average of the peak and valleys. So you may have non-conservative results if you use that. So if you read in the field file in FESafe, and if you store only the average at nodes data, then you cannot select any other options. But if you save the element nodal outputs, then you can select that too. But anyway, if you use that position equals to average that nodes to reduce the output file size, then you have a trade-off that you may have a non-conservative fatigue calculation results. Okay, so in Abacus, when we write a nodal output, we always extrapolate. No matter it is the elastic or the elastic plastic or linear or nonlinear analysis, we are extrapolating the stress tensor from the integration point to the nodal values. And if you use a linear reduced integration point, reduced integration element, then the integration point value will be just copied to the nodal values. And if you use full integration, then as you can see, top right, we are using trilinear extrapolation, which matches with the shape function of the element. And if you are using second order element, then you are doing the tri-quadratic extrapolation, as you can see on the left bottom diagram. And if you're using, so that's the how we extrapolate the integration point values to the nodal values. And there is a new element type available in 2016, which we have a kind of a surface stress improvement elements. For the TET, it was available in 614, but from 2016, we expanded that to the brick elements too. So in that case, actually, you don't have to extrapolate the integration points value to the nodes because that element itself has the integration points on the nodes. So in case we are using C3D8S, you have altogether 27 integration points. Okay, and on the other hand, Ansys only extrapolates the integration point value to the nodes when you do the nonlinear analysis. If you do the linear analysis in Ansys, the Ansys nodal value is just a copy of the nearest integration point value. So that's the difference between the Abacus and FE-Safe, Ansys. So overall trend is if you use Abacus for the, let's say, elastic FEA or linear analysis-based fatigue calculation, then Abacus overestimate the stress at the nodal point, which means conservative, than the Ansys-based linear elastic-based fatigue calculation. And number 6 is how you handle the singularity in the mesh. For example, if you have a distributing coupling attached to the mesh directly, then you may have, or if the boundary condition is too close to the where the peak stress is happening, then you may have the discontinuity in the stresses, so that you may have a hotspot in the fatigue calculation. In that case, you can ignore that hotspot from your consideration because that worst life is driven by the singularity in the mesh. So when you investigate the fatigue life in your structure, you should not investigate on those regions which has the singularity in the meshes. Okay, and whenever you are doing the fatigue calculation, we recommended we recommend you to use the Convergent Mesh, so that you already went through the mesh convergence study, and then once you get the Convergent Mesh, which means you don't have any serious jump in between the neighboring elements of the stresses and strains, then go through the fatigue calculation afterwards. So that may be the one of the important recommendation regarding the FEA concern when you do the fatigue calculation. Okay, and then try to make a set or the groups of elements as your convenience, so that you can easily distinguish when you do the fatigue calculation. You can create those kind of sets or groups based on the element sets or shell sections or material you used for those elements. So we always recommend you to create sets and groups. And then if you do the fatigue calculation, you can actually select some of the groups without doing any fatigue calculation as you need it. Okay? And it is actually a little bit conflict with the whatever the main purpose of developing the surface stress improvement elements, but whenever you need, you can create a skin on top of the solid body so that you can extract the surface stress accurately. So, and then after that, you can just write the stresses on those skins only in order to reduce the ODB file size, and you can analyze on those skins only when you do the fatigue calculation to reduce the computation time of VeritySafe. Okay, and my last tips is the post-processing. And some customer called me and he just complained about FE-Safe gives me 100 repeats as a live repeats, and when I do the contour plot, I have a different number. Why is that? That is from the averaging scheme of your viewer. No matter what kind of viewer or post-processor you're using, you may have some averaging scheme built in that post-processing tools. And Abacus Viewer is also by default averaging the nodal values so that you have a smooth, continuous contour distribution. So by doing that averaging, we are actually changing or the changing the whatever minimum value. So whenever you turn on that averaging, you have a different number than the FE-Safe gave you. So our recommendation is when you plot the log life, you do better use a reversed rainbow and the turn off the average to get the correct value of the life estimation. And the last topic is the using a lot of users using the FRF because that's very quick and the very easy to use. But we recommend to use FOS instead of FRF because of the following reason. So first of all, factor of strength, FOS calculation is actually iterative. It is not really a re-evaluate the fatigue life when you change the stress distribution, but it gives you more reliable and the more accurate estimation regarding the factor of strength. So you can actually assign that by using the that output assignment, and then you can set up that FOS analysis with the analysis options, and then FESafe will iteratively solve for that FOS values for you. And on the other hand, if you do the FRF, then what FESafe does is just calculate the current state of that specific nodes, and it just calculates the fraction or the ratio between the current state to the whatever target life. In most cases, the infinite life, but just calculate the ratio of those. And you may have 3 ratios. One is vertical, one is horizontal, and the last one is a radial. And FESafe reports all those 3 plus the worst FRF, which is the minimum of the all those 3. So if we just consider compare those 2 methods, FOS takes a little bit more time than the FRF, and because it's an iterative process, and because those FOS calculation is more accurate than the FRF, you can actually apply it to the both of the low cycle fatigue and the high cycle fatigue. And you can use both of the FOS or the FRF with any of the algorithm. That's common, but because of that difference, we just let user think about using FOS instead of using FRF. Okay? And the next topic is
Okay, so coming to the next tip, as you might know that for any fatigue analysis process, one of the input which is required is the material properties. So whether you are using a stress-based algorithm or a strain-based algorithm, you have to have those material parameters into it. So this topic tells that how to get the best out of material database in FESafe. So if you have a new material and you want to see that how can you get fatigue properties for that new material, then there are few ways you can approximate that material property, and one of the way is to see our existing literature resources, and those are either using a FESafe system database file or using a external material database. So this is the first one. Second is you can use the approximation, in which you can use either a Seeger approximation method, which is available inside FESafe, or you can use a 4-point method, which is available outside FESafe in the literature. You can also discuss with your metallurgist or to see like if he or she can identify the correct material properties based upon the ultimate tensile strength or the elastic modulus for that particular material. And finally, you can do the testing. But in this particular case, we'll be discussing on how can you use existing literature source, like how can you use our 2 material databases, which we have. So when you are searching for any particular type of material, then you can search it by many different ways. You can search the materials by mechanical properties like elastic modulus or ultimate tensile strength. You can search it through chemical composition. You can search through the microstructure of that material. And finally, you can also search through the specification, like what is the ASTM number for that particular material. And based upon that also, you can search the material in our material database. So this is the video which will show that how basically you can use our material searching in FESafe. So if you can start the video, please. Okay, so this is how our FESafe graphic user interface looks like, and on the top right corner is their material database. So in that, there is a system database and there is a cast iron database. Both are log database, so you will not be able to edit the material. So if you want to edit the material, then you have to move those material to the local database, and in the local database, you will be able to edit the material. So that's the local database, how. And then there is another feature which I like about this material database, and that is the filter option on the top. And in that filter option, you can choose that about the steel, or you can choose the cast iron, and you can see how many steels or cast iron are there. And if you will choose on aluminum, then you will see that there are quite a few material which is available in our this FESAFE graphic user interface. But there are a lot of material in aluminum which is available in our external material database. Then you can also search the material by a number. So in this particular case, I'm searching it by the number 1008. And if I search the material, then there two material pops up. First material is mainly because there is an hardening exponent, which is 1008, which is one of the material property of this particular material. We are not interested in that. What we are interested in is SAE 1008. And if we just click on the arrow, then you will see what is the algorithm this material is using, which is Brown-Miller-Morrow algorithm. Also, it tells you about the constant amplitude endurance limit. It tells you about the elastic modulus Poisson's ratio. And it also tells you the ultimate tensile strength. It gives you the cyclic stress strain curve parameters, as well as the parameters which can be used for the strain life parameter. As well as it will also give you the parameters for the stress life. So you can see it has all the material information which is needed. Now let us go to our external material database. So this is external material database is already open for you. And in this external material database, you can search the material by name, you can search the material by type, or you can search the material by chemical composition. So there are many different ways by which you can do it. So first of all, let us see like how many aluminum are there in our external material database. So I can just type aluminum and say go. And once I say go, then you can see that there are a lot of materials in this external material database which are available to the users which they can take advantage of. Now, if I want to just see that how many cast aluminum are there, then I can type on cast on the type search menu and say and on the Boolean expression. And if I will use both of them, then it will refine my search to some value. Then so once I go over there, then you can see that there is this specification number which you will have the information about. You will have the information about the heat treatment. You will have also the information about the test conditions. So this is all the information which is available from the literature sources which we have put it for you in the external material database. And also the testing specimen which was used, it has the information about the chemical composition, what are the different chemical composition do you have, and so on and so forth. And now we are searching for a gray iron. So in this particular case, we will just type a gray in the material class and say go. These are all the gray iron which we have, and it has all the information about the gray iron which we could collect from the literature sources. And then we can choose the chemical composition, and in this particular case we are choosing the carbon content of the gray iron going from 3 to 6%, as well as we are choosing for the manganese greater than 0.5%. So you don't have to fill the other side of the inequality. And if you will say go, then it will filter more some of these materials, and which will show the chemical composition of it, as well as it will show a lot of other different parameters for this particular, any particular type of material which you will be interested in. So what we can then do, we can take these three materials, which are the three different specimen size, and we can export the DBase file for this particular type of material. We can also search the material by the Brinell hardness number. So we can type the number as a Brinell hardness and then say go, and then out of these materials it will search for the material with the Brinell hardness number between 100 and 200. And these will be some of the materials which will be there, and you will be able to get that information. So this is a very quick check to see like what are the materials which are available. But Brinell hardness number is not a very good property to check overall, because if I just use a Brinell hardness number as a search without specifying anything, then these are all the materials which I will have. It will have the material for the cast steel, for the gray iron, so that it will have lot of different versions of steel. So, so you can use this parameter to filter it, but for originally searching the material, you have to use either ultimate tensile strength or the elastic modulus. Yeah, so now coming to the another specific material, which is like a steel. So we can search for that material which is steel, and after looking for that, we can look for the quenching and treatment. So the quenching is always represented in the external material database by the letter Q. So you can search for in the heat treatment letter Q, so that all the steels with quenching and treatment will come into the material search. Also, you will be able to do normalized heat treatment, and if you will do that normalized heat treatment, then the materials with the normalized heat treatment will come in the database. Okay, so now we are searching for another type of material, which is 24 chromium molybdenum, and there are these different type of materials which are there for that particular case. And now for this particular material, we can see how this material is called in all over the globe, but how it is called in American or in Euronorm or in other part of the world. So that is another, again, always a useful information to get. And you can also go to the chemical composition and see which of them is having a low sulfur content. So you can type that sulfur value which you will be interested in, and you can see these are the materials which are there. And you can then select all these materials, and you can again send this material to the and can create a DBase file for that. So we are creating the DBase file for this low sulfur content materials for 24 chromium molybdenum. But now with the power of computer, we can then just go to this material database and open the database. And right now we are interested in opening the database for the 3 specimen which we have done before, and for those 3 specimen database file, we are now plotting the strain life curve. And so we're using our material plot functionality in FSF. So for that 3 different materials, we have those strain life curve which we can plot all of them in one single plot. And once we do that, you can see that it is for the fatigue point of view, the lower specimen has given the better life, so it is more advantageous compared to a large specimen. And that's what has been shown based upon this strain life curve.
Okay, I must admit, I took a sneak peek through the feedback forms in the coffee break, and the first one I picked up said, "No more welds, please," which puts me in a bit of a difficult position here, but I'll try to do my best anyway. Right, what's the difference between welds and the base metal? This is perhaps something that is not entirely understood by all the analysts, so I'll just go through the differences fairly quickly. What's similar? First of all, we use the same cycle counting. We use the Rainflow cycle counting algorithm for converting or cyclic counters. We use the minus rule to sum up the damage. So it's the same as for the base metal. The damage parameter is very similar. It's a stress range. We can calculate probability of failure. We can use the variable amplitude loading, and as in case for the base metal, the variable amplitude loading affects the endurance limit. So these are all similar cases or similarities between the base metal fatigue and weld fatigue. What's different? Well, first of all, for welds, getting a better material does not improve a weld life, unfortunately. It's a common practice. If your component fails due to fatigue, you just reach for a better material and hope that it will save you. And in most cases it would. Unfortunately, that's not the case in welds. Because the welding process essentially melts the metal, it reverts it to its basic structure. Therefore, the strength of the weld, whether you start with a common steel or a high-strength steel, the strength of the weld itself will be very similar. What's more, it actually can have the adverse effect, because if you use a high-strength steel, welding of that steel will be more difficult. So getting a good quality weld on a high-strength steel may actually be more difficult than getting a good quality weld on a fairly low-grade steel. So it may actually have the adverse effect. There is a common factor of joint geometry effects. This is taken from the nominal stress approach based on British Standard 7608, where different different weld geometries, are assigned different classes, so they have different fatigue strengths. And this is what the Battel's structural stress method addresses using the structural stress and then corrections for equivalent structural stress. There are no residual stress effects, though this has been questioned today. In general, it is assumed that if you have an S-welded state of a weld, there is no effect of a residual stress or a mean stress, which is not true for base metal. There are effects for the plate thickness, so the thicker the welded plate, the different the light will be. And again, this is not the same for base metal. So these are all the effects you will need to consider as an analyst, and that's why weld fatigue methods are different to your base metal fatigue calculation methods. Surface finish effect. We say usually that the roughness of the surface will have impact on your fatigue prediction. That's true for base metal, not for welds, because the welding process inherently introduces small cracks, what JK said before the break. So any surface roughness will not be enough to overcome the effects of inherent cracks in the weld. So essentially, we ignore this effect. And last but not least, this is something that as analysts we tend to ignore, so-called insignificant attachments. And I'll use a case of the Alexander Kielland platform as an example here. This is a drilling platform. This was a Norwegian drilling platform operated on one of the oil fields in North Sea. As you can see, the platform is stabilized. The laser pointer doesn't work, but you can see that the platform is stabilized on, I think there were 5 legs. As you can see, there's big pylons there, red and white, you can't miss them. At some point, one of those pylons broke off. That made the platform unstable. It tilted firstly, then capsized, and then sunk. Bit of a problem, as you can imagine. A huge investigation followed. What they found out was that the breakage of the support pylon was due to fatigue. That's why we're here. What's more interesting, it was a case where workers putting the platform together on the sea use something called a hydrophone to talk to the workers under the surface. And to simplify their work, they welded a simple attachment for the hydrophone into one of the supporting struts. Oh, there you go. They welded a tiny little bracket to put the hydrophone on as they worked. This was a 6mm weld. 6mm in your money is 1/4 of an inch, less than 1/4 of an inch. From that, a crack started, propagated, broke one of the supporting struts, made all the structure unstable, resulted in breaking off one of the pylons and the platform capsizing. A 1/4 of an inch weld sunk a 300-foot platform. And this is something that, as analysts, we rarely think, these insignificant welds. When it comes to welds, there is no such thing as insignificant. Okay, there was a bit of a talk from JK and others today on how we can improve or how we can consider weld improvement techniques in our calculations. I'll show you how to actually enter these improved curves in FESafe. This relates both to the nominal stress approach with BS7608 and a Verity structural stress method, as you have seen earlier today. So there is different curves, you may want to enter them and use them in your calculations. So starting with BS7608, first of all you need to create a new database to store your materials. Then the easiest way is to just pick a material from one of the existing ones and copy it to have a starting point. Renaming the material, of course, including the weld class, any effects accounted for, and so on. The algorithm to be used for the nominal stress approach would be the principal stress algorithm with no mean stress correction. We're now assuming as welded state, so there is no effect of mean stresses. You can remove all the strain life parameters because weld fatigue is based on stress-based approaches. Set the endurance limit to 100 million cycles. This is typical for weld analysis. This is common for BS7608, for IIW, and for Verity. And then you create the endurance curve, stress life curve. However, what is important here is that you convert data from a standard where it's presented as a stress range into the quantity that's expected by FESafe, which is stress amplitude. So essentially, as you read any stress data from either IIW or BS7608, you need to divide that value by 2 before entering it into our database. It's a simple process to do, really. So these are the important, well, you can barely see them on the screen there, bits. Rename, change the default algorithm, change the endurance limit, enter the endurance curve data. For Verity, it's a very similar process. You take the existing Verity database. Because it's read-only, you need to make a copy so that it's unlocked for you to edit. Delete any unused curves, rename the welds, indicating the improvement process or probability design criteria, and then again enter the new SN tabular data. Again, this time in form of a stress range versus life. For Verity, we treat it separately, specifically, so in this case you enter the data as stress range, not stress amplitude. So you can add the improvement processes, as JK discussed, you can add new materials, and so on. And the tip number 1, top tip, and that's because there has been a lot of complaints about the usage of Verity method. It's been quite consuming when it comes to manual definition of welds, and that's why we have developed the Weld Finder. Now we have developed it, we really want you to use it. That's the idea behind it. It works for both solid and shell meshes. It allows automatic configuration of seam welds and spot welds. For seam welds, it uses an element set as a starting point, an element set representing the weld fillet or the weldment. The through thickness nodes are identified. Toe, root, throat, crack planes are determined automatically. For spot welds, all connector or beam elements are detected automatically as spot weld representations. Number of sheets is automatically detected. Sheet thickness is automatically detected, and so on. So the weld finder can detect the plate thickness, or you can specify it manually. So if you have a variable plate thickness, the code will actually automatically take it into consideration. So if your plate thickness varies along the weld, the code will automatically take that into consideration. And that's a fairly new feature that wasn't possible before. It also can consider the throat depth rather than thickness if you're considering the throat failure, and so on. It's based on an element set that represents the weld fillet, which is shown in green there on the screen. If there is enough detail in your model, the weld finder will attempt to find the toes, throats, roots, and so on. How does it work? You start with, well, this is a screenshot from 2016. It will look slightly different in 2017, as David mentioned earlier today. You go to the Define and Analyze Weld Geometry menu. A dialog pops up where you add a new line weld. Essentially, when you start up, you start with a single parameter you need to edit. It's just specify the element set representing the weld. How the weld finder works, it assumes that the weld fillet is reasonably well modeled, represented by elements that are approximately at 45-degree angle to the base plate, with the tolerance, as you see on the screen, 25.5 degrees. And it assumes that the cross-section of the weld is reasonably triangular. It does not need to be exactly a triangle, but it is reasonably triangular. If it's more complex shape, it may have some issues finding or defining the root of the weld. It will find the toes fine. It may have some difficulties identifying the root of the weld. So if you want to add a little bit more, you can select or you can open up the additional configuration options. Those that can be useful are, first of all, what type of a crack you want to consider. By default, it's set to consider toe failures, but you may want to also make it to detect the throat failures, fusion plane failures, and so on and so on. And that's defined using the first four options. Second thing, by default, the code will try to detect the thickness of the welded plate automatically, and also considering variable thickness. If that's not what you want, you can specify the thickness of the welded plate manually, and that's the second, and that's the second parameter there. From the top, you can barely see that. And the third one, which did not fit in the screen there, is the weld symmetry. If you modeled your component using any symmetry boundary conditions, for the algorithm, it's essentially treated as the end of the weld. Therefore, it would apply a weld end correction with stress concentrations. If that's not desirable, you may want to indicate that there is a symmetry condition at the beginning or the end of the weld. And that's slightly, you need to scroll the option list down a little bit, but it's there, believe me. Once it's all done, you can run the analysis and you can admire the results in form of a nice, colorful contour plot. In this case, we've only analyzed the toe failures. If you chose to look at throat failures, there would be also results there on the weldment, and so on. Which brings us very nicely to the end of the top 10 tips and tricks gathered from our customers. Normally, I would ask whether there is any questions, but since we have planned for a Q&A session now, I will not. I will invite David and Giovanni to join me here on the stage. And to start off, we'll try to answer questions that were put in the questionnaire. So David, if you care to start.
Okay. So if you do have any FE-safe rubber questions, you're welcome to ask. those, and Will Mars will pop up and answer them. You can come on up if you want. We don't have any of those right now, Will, but you never know.
I'll just...
Okay, you'll do it on an ad hoc basis, right? So, hang on, which... Right. So the first one for me is, are there any plans to implement Verity analysis in the Ansys Workbench? Sorry. So are there any plans to implement Verity analysis in the Ansys Workbench? And I'm going to combine two questions here because it's going to be the same answer. Will rotate, so IFE-Safe has this rotate option, will be made to work with Ansys Workbench. So the answer is maybe, right? And it really depends on how many people request it. All right, so if you don't, I will enter these as requests, okay, into our request database, just as an indication for our planning for IFE-Safe 2018. We have like 320 of them already, and we can probably only get through maybe 50 or 60. Okay, so you know, if you want to lobby your friends to also ask, then it might go up on the list, right? So Wayne Tanner asks, is there a standardized or recommended method for short fiber plastic fatigue? And have these methods been validated? All right, so the guy who really should answer that question is, I keep moving away from the mic, sorry guys. The guy who should really answer that question is not here today. His name's Anders Winkler, and he has, I mean, he spent a career doing a lot of working on some of these things at a company in Germany for about 10 or 15 years. So he has a lot of recommendations on how to do that, and how to do that also with IFE-Safe, and what maybe some more advanced methods are. So he has what he calls what he calls the basic method. He regards that as a sort of starting point for a standard method. And he has a lot of confidence in it based on experience with it. Wayne also asks another question. When will multi-axial shear be included in Verity? So I did mention that a bit earlier. We have done a lot of the work on this already, but we needed to conclude our agreement with Battelle, because the old agreement ran out at the end of last year, and we needed a new one. Now that we have a new one, we can start chatting with them. There may be some IP-related issues we have to negotiate on this. I'm confident we'll get through those, but it could take a little while, and then we will be able to release it, hopefully in the new year sometime. So do I have another one? Okay, so here's a question, couple of questions. It says, how can you get meaningful results if you don't understand your loading? And the second one is, are there any good tools for understanding loading and correlating to test? Now, I'm going to say, who do you think asked this question? Any guesses? Any guesses?
Tim!
Oh, of course it's Tim. Because we'll start do indeed have some very good technology.
He's clever, you know? That was clever. There's one question here. Well, that came from Jay. Has any work been done to compare and correlate TCD and FKM stress gradient methods or across different geometries, and maybe came up with a conclusion on what's more conservative and which one is the best, perhaps? Well, we have just released the first FKM, so it's quite new to us. So we haven't had that much time to compare FKM with everything we've got. But I would go further and say that this is a very tricky question because FKM can be a little subjective, depending on depending on the severity of your usage. If you're killing people, or if your component is will not kill people eventually, or depending on several other factors that may be subjective to the designer. So that may introduce a factor that may turn the comparison a little tricky. But what we can do as an exercise, and I take that as a suggestion, is to compare the stress gradient method present in the FKM with the DCD. So yeah, well, we're going to do that, and maybe next year to come up with an answer, or earlier than that, and then we can keep talking by email. So that concludes, or we have another question? So Pavel has two questions?
Right. My questions, you can probably guess they're related to welds. So is the automatic weld detection done in FE Safe or the FE software? I hope you can now all say that it's done in FE Safe. We've done it. It's brilliant. And then the second question to follow up is, how are the welds unorganized? By default, all the welds will be put into a single group as welds. However, they can be split depending on the crack or the failure mode or the crack plane. So they could be split into toe failures, root failures, fusion plane failures, and so on. Or you can go and split them individually. So you can have a single entry or a separate entry for each single weld. It all depends on how you want to configure the analysis. And the second question is, how does fatigue in brazed joints compare to welded joints? And unfortunately, Dr. Hong from the Battelle Memorial Institute had to leave a little bit early. He'll be the best person to answer. But I have asked him this question in the coffee break, and he said that essentially, and I quote, "We have the method if you have the data." So the methodology works, but there is not enough data to incorporate it as a commercial solution. So if you have any data and the fatigue data on brazed joints, we were more than happy to put that in, but at this point, we simply don't have enough data. So that's all the questions we had in the questionnaire. Are there any questions in the room? Well, there you go, Tim.
Hello? So I'm not going to be a smart aleck, okay? I was actually wondering about the weld finder, because it looks like really cool technology.
And it is.
All the meshes that you had on the screen were nice regular meshes that you wouldn't need the weld finder for. So how does it work with kind of free meshing and finding through the thickness and all those good things?
Okay, the first question, even if you have, or the first answer, even if you have nice meshes or simple welds, you still would want an automatic weld finder if you have hundreds of them in your component. You don't want to go in and configure them one by one. But that's not your question. For more complex geometries, as we had an initial release of the weld finder, you may remember that was, I think, 2 years ago, if I'm not mistaken. Yes, it coped well with the simple geometries. There were a few hiccups and bumps in the road for more complex geometries. As we get more feedback from our customers, from our users, we incorporate more and more checks into the complex geometries. I think it is very robust now. It can cope with really strange geometries with curvatures and so on, both curved base plates and curved welds, and it copes with them reasonably well. The only thing, as I mentioned, is if the cross-section of the weld is far from kind of triangular, the code may not be able to find the root of the weld, because there may be multiple points that it may be referring to as root. So that's the only sort of ongoing challenge that we're still trying to address.
So what about the through thickness mesh? Because I was seeing those through thickness meshes were nice and perpendicular, and you're not generally going to hit them.
Ideally, that's what you want, because you want to base your nodal extraction on a reasonably good quality mesh or reasonably structured mesh. But what we incorporate is essentially ray tracing with a cone. So we put a ray sort of normal to the surface of the weld toe, and there is a cone tolerance, starting with the weld toe and then expanding as you go through the thickness, trying to identify nodes as you go along through the thickness. And that's configurable, so you can make it as narrow or as wide as you want. I wouldn't advise going too wide, though. Do we have any more questions? There's a question there at the back.
So the question I have is regarding skinning a model with membranes or shells. Do you use extract at the nodes or at integration points, and will it work for all orientations? Because I tried this some years ago and had some problems with some orientations of elements.
I'm not familiar with orientation of elements. Whether you use integration points or nodes at this point would not matter, because you are reading off stresses on the surface, which is what we want. So whether you use integration points or nodes, it probably won't make much of a difference. When it comes to orientation, I'm not sure. I'll have to discuss that offline.
Well, they are. I mean, what kind of problem did you have with the orientation? Because
David, if you can.
Yes.
I mean, at each node or integration point, it's going to have its own orientation. So I'm not quite sure why you should have an issue with orientation. Now, one thing you do obviously have to consider is if you have contact or pressure loading on the surface, right, membrane elements won't have that normal direction stress included in it, right? So you have to have truly plane stress conditions at the surface for the membranes to be effective.
No, they were just normal continuum elements with no contact. But
Right. So it should work pretty well because at the surface you will always have, if there's no normal or shear loading on the surface.
This was some years ago, but I believe
Yeah.
it had something to do with the direction of the direction of the element being. There was a bug. I can get you send you an email on what they sent me back. It was some years ago.
Yeah, I mean, this has been a fairly common practice with Abacus users for, I don't know, 20 years. So I would be surprised if it didn't work pretty well. Okay.
Do we have any more questions? So we have these two bright lights there, so I can't see any raised hands. No? Okay. That's it then. I'll invite Alan back on the stage to close the day, if that's okay. Oh, he seems a little bit surprised.
Well, I'm not sure what I need to say. I can say it from here. I hope you've had a good day. The feedback forms are going to be valuable to us. The feedback will help us decide what we want to do next year. So we're interested in your views. Please make sure that you drop them off before you leave. And for those of you coming to the RUM tomorrow, I look forward to seeing you there. Otherwise, thanks to the team for a great day, and I hope you enjoyed it. Thank you.